Hi, this is our fifth video in chapter 6. This is on geostrophic winds, and I'm going to start with what you already know, and then we add to what you know. This should look really familiar to you. It's a surface map, and we've been talking about surface winds crossing isobars due to the pressure gradient force, which we abbreviate as PGF. The pressure gradient force will go from high pressure to low pressure, and it should be directly from high pressure to low pressure, but we've already learned that other forces act beyond the pressure gradient force. Those other forces include friction and include the Coriolis effect, so it makes curving motions out of high pressure zones, and it makes curving motions into low pressure zones. And you know this too, that where the isobars are tightest, the winds are fiercest, and where the isobars are broadest, the winds are gentlest. Now, on the other hand, an upper level map doesn't look the same as a surface level map. And in fact, in an upper level map, there's no motion in toward or out of a high pressure zone. There's no motion in toward a low pressure zone. Why is that? Why are these winds parallel with lines that look like isobar lines? Those lines look like isobar lines, and they are not isobar lines. Let's go over what they are. They are contour lines. Again, let's start just above the surface layer, like we did in the last video, where we looked at the 850 millibar level. At this point, we're going to look at the 900 millibar level, even a little bit lower than where we were before. And we're going to look at pressure gradients at that low altitude, just above the surface level. In fact, probably about 300 feet above, about 100 meters above the surface. Like you know, the horizontal movement of air will go from a higher pressure to a lower pressure. In this case, it will produce a southerly wind that goes from the south to the north. Here's our compass rose down here. Just above the surface, as the wind accelerates, it starts here and accelerates, the Coriolis effect does tend to deflect the air to the right. And as the wind vector continues to accelerate, and when I say continues to accelerate, now it's not only changing speed, it's changing direction to the right. That will make the Coriolis deflection continue and increase to the right. So we're going from position 1 to position 2, a little bit more to the right with position 3. You're going to the right of the direction of the movement of air or the wind. The wind is in purple. You will continue this rightward movement until the pressure gradient force and the Coriolis force balance each other out. When they balance each other out, you will find that the wind is no longer accelerating. It's no longer changing speed. It's no longer changing direction. As a result of that, the force on that is a net force of 0. Because remember, force is mass times acceleration. If you're not accelerating, you don't have anything to multiply by, your force is going to be 0. When the wind is parallel to the isobars at your altitude. Let's compare altitudes. Let's compare upper level wind altitudes, skyscraper wind altitudes, and surface wind altitudes. We already looked at the upper level wind altitude. Now we're going up to about 3,000 meters. That's going to be approximately 750 millibars of pressure. And we note up there that there are winds that are parallel to what we call the contour lines. We'll get into that in a second. We also know the skyscraper level because we've already studied that. And we know that if you took 2 columns of air and you heated one of them, you would have more high pressure above you at about 1 kilometer. And if you cooled the other column of air, you would have very little pressure above you. So we have high pressure aloft and low pressure aloft. When we move from high pressure to low pressure on the pressure gradient, you're going to get some Coriolis effect. However, there is a lot of friction due to these skyscrapers that will slow down the velocity of the wind. Hence, it will slow down the effect of the Coriolis force. And so you won't get that much of a pull to the right. And in fact, we can even take this down to the surface level where you have a lot more friction because you not only have buildings, but you may have hills, you may have trees, you may have fields with sunflowers and so forth. So you may have high crops. In that case, friction is going to play a real role in slowing down the velocity of the wind and the wind vector and in minimizing the Coriolis impact. In fact, at the surface, the pressure gradient force gets deflected not by 90 degrees to make a parallel wind, by about 60 degrees. So you're actually 60 degrees from the vertical and about 30 degrees from the parallel wind. To sum up, winds on upper level charts, very little friction, so faster winds, more Coriolis effect. Surface winds, lots of friction, less Coriolis effect, and therefore the winds tend to cross the isobars rather than running parallel with them. And let's talk about that a bit more before we get into the big upper level charts. Those straight line winds are known as geostrophic winds. They're winds that are parallel to evenly spaced contour lines. We're going to be talking about contour lines in a second, and you know the net force is going to be 0. The way to remember geostrophic as a word, geo means earth in Greek, like geology, like National Geographic. Strophe means turn or bend in Greek. Okay? Now, let's get to the upper level maps. You know that they're going to show geostrophic winds here that are parallel to evenly spaced contour lines. And you are going to find out that zonal geostrophic winds are generally straight from west to east. They clear out surface storms rapidly. On the other hand, meridional winds, hard to say, are basically north to south winds or south to north winds. They go along the direction of the longitudinal meridians. That's why they're called meridional winds. These can be very, very high-speed winds, but their movement west to east is slowed down by this north-south direction. And so they tend to stall over stormy areas and intensify stormy areas rapidly. When I see these meridional winds, I am wondering about storm formation across the country. In addition, these contour lines can predict wind speed much like the isobar lines predicted wind speeds. When isobar lines were tight, you had high wind speeds. When contour lines are tight, you have high wind speeds. Here's an example right here. Tight gray contour lines. High winds. Winds up around 75 miles an hour. On the other hand, where you have gray contour lines that are far apart, you have much lighter winds, about 9 to 14 miles an hour. Why is this the case? Why do isobar lines, you understand about pressure gradients in wind, but contour lines are not pressure gradients. Contour lines are one pressure level. In this case, it's 500 millibars, about 5,000 meters in altitude. Why would the same tightness and looseness of these lines impact wind speeds as well? Think about what's happening here. When you have a broad space between altitudes of 500 millibars of pressure, you actually have a slow horizontal change in altitude. And wind is a horizontal air movement. So if you have a slow horizontal change, you're going to have a slow horizontal movement and a slow wind. One other point. When you have atmospheric low pressure as the side of the pressure gradient force that you're moving toward, and you have atmospheric winds that are running parallel to your contour lines, it turns out that your low pressure system in the atmosphere is always going to be on the left. And we know that the atmospheric low pressure systems are much more predictive than the surface low pressure systems. So it's a really handy thing to know where the atmospheric low pressure systems are. They are always going to be to the left of the way the wind blows. Let's explain that a little bit more because you could walk outside and figure it out. How do you know the atmospheric wind direction? You take a look at the direction the clouds are moving in. The clouds are up in the atmosphere. The clouds are being driven by the atmospheric wind direction. And therefore, if you know that the clouds are moving in a geostrophic wind that is parallel to the contour lines, you know that your atmospheric lower pressure system is going to be to the left of the direction of your cloud movement. So you can walk outside, check out the clouds, check out the direction they're moving. Get yourself so that they're moving from your back to your front, and then look to the left, and that's where your low pressure system is. It's really going to be helpful for us. If you think about, and let's think about the atmospheric low pressure systems. Atmospheric low pressure systems tend to be sinking air. And that sinking air brings in a trough of air that is compressing and warming and bringing drier weather. Think about our work with Denver and with Maui in the lab. When we thought about the sinking air on the Denver side and the sinking air on the leeward side, we thought about compressed, warming, and drier air. Think about this a bit, stop the video and take a look at it, and I hope to see you soon.